Alright, so in the first lecture I talked about the basic idea of capacitance, what it means, and now what we're going to do is we're going to look at how we can find the capacitance of something other than a parallel plate capacitor, and we're going to focus on the cylindrical capacitor. Now you can have a capacitor as pretty much anything as long as there's a charged object. There's going to be one problem in your problem set that has a single isolated sphere that's charged. In that case, infinity is the other, essentially the other plate. So yeah, the infinite void. That can be used. Okay. Last year, I think that we used the Van der Graaf generator. That's an example of a capacitor with just a single charge source. If we touched it, became essentially part of that capacitor. And then you saw the effect that we might have on other things like the lights because of the field we were generating. And they then acted as the other plate of the capacitor. Excuse me. So we're going to focus on just a cylindrical one now. And the cylindrical one would be a precursor to an even better type of capacitor, which would be like a spiral type. So just to show you what I mean by that, a spiral type would look, something like this, where that's one plate, and then like this is the other plate, like that, and this might be the negative terminal, and this might be the positive terminal there. Okay, so you'd have a positive, negative, and then they just wrap around each other. The advantage of this is that you get a lot of area in a small space. Okay, and you don't really care that these two plates are close together because often that's what you want anyway. A cylinder allows you to get a bigger area than a parallel plate capacitor would allow in a smaller package. Not as small, though, as if you had more of a spiral shape. But that's a little bit too much for us. So this is going to be a cross-sectional view of our cylindrical capacitor. We're going to have an inner metal cylinder. Doesn't matter if it's hollow or solid. You know that the charges are all going to congregate on the edge of it anyway. And then we're going to have a cylindrical shell surrounding it. And I'm going to give these some sizes. So this is going to be a size of A. That's going to be a size of B. So we'll call that our radius of A for the smaller one, radius of B for the other one. And I'm going to charge the inner cylinder with a charge of plus Q. And the outer cylinder will be charged with negative Q. And these, of course, will be uniformly distributed around the entire cylindrical shell. So if you imagine the shell kind of goes back into the distance, however far it ends up going. Now, we can draw our electric fields. Our electric field should do something like this, radiating outwards from the positive towards the negative plate, okay? And these are thin shells, so we're not really worried about inside it, though of course inside of the shell would be 0. So just to reiterate, this surface here, the inner one and the outer one, are two completely non-touching surfaces. There is air or a vacuum or something non-conducting in between them. So I'm ultimately going to try to find capacitance, which is Q over V. I already know Q, so that's one thing checked off my list. If I want to find V, I'm going to use delta V equals the opposite of the integral of E dr. And in this case, I'm going to be going from, let's go from B to A. So B to A. So that means that I'm going to go from a point out here to a point in there. Why? I'm not sure. That just happens to be what's on my paper. So we're finding the difference in potential from B to A. The advantage of that is that it just gives me a positive potential when I do that because I'm going from some negative charge to some positive charge. So in order to do this effectively, though, this equation here, I need to find out what is E. That's easy enough. I can use Gauss's law. So at any point in between these two, I can draw a Gaussian surface. And in fact, what I'm going to do is I'm essentially going to be drawing, in order to execute this equation right here, I'm going to be drawing a Gaussian surface at every instant r between the inner and the outer surface. But I can just get the generic equation, which will be E times the area of this. And remember, this area is extending back, okay, into that distance. And so the area of that is going to be equal to 2 pi, I already did a pi, 2 pi RL, where R is that distance and L is however long back I've made my Gaussian surface. And that's going to be equal to the charge enclosed. Now the charge enclosed could go one of two ways. The easiest way to do it is to just treat this as a line charge, actually. Okay, so in terms of the actual length here, I've made that up, but I don't know the exact length of the cylinder. I'm going to assume that it's infinite, but it very well may not be. So I'm going to say that, for my purposes at least, it's got a charge, it's not working there, linear charge density of Q over L, whatever that total length of the capacitor happens to be. Okay, so that's the basic idea there. Now, when I go ahead and I divide this by epsilon naught, first thing I notice here is that I'm going to get the L's canceling out. Okay, and so then I can get that the electric field is equal to lambda over 2 pi r epsilon naught as my response to this. Now the other thing that I can do is if I want to, I can rewrite this as the total charge over 2 pi r L epsilon naught, where L is the total length of my cylinder. So the actual geometric property, the real geometric property of my cylindrical capacitor. So this is my equation for the electric field. Now I go back and I pop that into my my equation for the change in the voltage. And for that I'm actually going to go over to another page. So I had electric field as a function of R, this is in fact as a function of R, equals Q over 2 pi RL epsilon naught, and delta V is equal to the opposite of from B to A of my electric field, which is Q over 2 pi RL epsilon naught dr. So you can see that I have everything as a constant except for the divided by R and the dr. So this is just going to end up being Q over 2 pi L epsilon naught times the natural log of R evaluated from B to A. And there's a negative sign there. Now if you remember how you deal with natural log functions, subtraction of natural log of 1 minus natural log of 2 is really just the same as division. So I'm going to end up getting negative Q over 2 pi L epsilon naught natural log of A over B. Now if you take the natural log of A, which is smaller than B, you will get a negative value. So we might as well just rearrange this to say Q over 2 pi L epsilon naught natural log of B over A. Okay, so that's how we solve for the delta V. For capacitance, I want to do Q over V, so I just take Q over, well, it's Q times the natural log of B over A, over 2 pi L epsilon naught. So you'll see that the Q's cancel out, and this stuff flips over to the top. So I end up with a capacitance that is equal to 2 pi L epsilon naught over the natural log of B divided by A. And that is how you find the capacitance of a cylindrical capacitor. Notice that depends on the three geometric properties of the cylindrical capacitor, namely the length and the inner and outer radii. of the cylindrical capacitor. It does not depend on anything else so far. So that's all that's involved there. All right, in the next video, I'm going to talk a little bit about energy for capacitors, and then I'm going to talk about dielectrics.